So what we want to talk about today are anhydride reactions. Anhydride reactions, as the name suggests, is without water. So when you have water as one of the reactants, you can pretty much assume that the substance that's reacting does not have water in it, and it's being, I guess you could call it, added into the system. It's often advantageous to think of water as hydrogen hydroxide, HOH, in these reactions, and sometimes we'll refer to them like that. Non-metallic oxides, these are non-metallic oxides, or acidic anhydrides, as they're often called, plus water yield acids. Now these anhydride reactions are very rule-based, so you really need to know your rules on this when it comes time for these quizzes and for doing the worksheet. So if we've got CO2 and it's reacting with water, remember water is one of the reactants in an anhydride reaction. What this is going to do is actually combine together, and what we're going to end up with is H2CO3. Now, H2CO3, we were dealing with water again, so now we have to go back to the situation where we're worried about what's going to ionize in the water. If H2CO3 were a strong acid, this would ionize or split, and we'd have to write it that way. So we have to start watching for that again. We didn't have to worry about that with combustion reactions or with addition and decomposition reactions. Now, if we have a metallic oxide, these are called basic anhydrides because when you add water to them, they yield bases. For instance, if we've got solid sodium oxide, and one thing to remember is that if it tells you that something is solid, even if it would split when it's or ionize when it's added to the water, you will not show that in the reaction. So we've got Na2O. Guys, I'm seeing a lot of people not finding charges. If sodium is a +1 and oxygen from oxide is a -2, then it's going to take two sodiums to satisfy that oxygen in the formula. So Na2O is added to water, and when we do, we get a base. And you, from looking at this, I feel like you should be able to figure out what base would be formed. And it is sodium hydroxide. Now I'm going to write it like this, but keep in mind, sodium hydroxide is in water now, and sodium hydroxide is a strong base. I told you we had to worry about what would split or ionize in water now, and sodium hydroxide would. So we're going to have to rewrite this in its ionized form. So we're going to get Na and OH minus split from each other or ionized. Now don't forget, if it splits, it gets a charge. That's our little saying, so don't forget that. We also need to balance it. Looks like we need 2 for the sodiums. And if you'll look, we've got 2 hydrogens and 2 oxygens on the left-hand side. So if we put 2 hydroxides, we'll be good there. So that's our basic anhydrides or metallic oxide reaction. Now, metallic hydrides, if we add water to those, as it said here, we're going to get metallic hydroxides again. We're going to get a base. But this time, we're also going to get some hydrogen gas. So let's take sodium hydride, for instance. Sodium hydride, a hydride is something in which the hydrogen has a negative charge. It's written at the end. And that sodium hydride is added to water. Now, again, it's often advantageous to think of this as being HOH, because if you do, you can think of this a little bit like a double replacement reaction where the hydrogen and hydroxide are switching places. Those end elements are switching places. So what we end up with then is the sodium with the hydroxide, and we end up with the hydrogen gas. Again, we're in water, guys. That's the whole point. So that sodium hydroxide cannot stay like this. We have to write it in its ionized form. The hydrogen gas won't split. It's in the elemental free state, but the sodium hydroxide will. So that's how we're going to have to write it. We get a similar result if we take a highly active metal from group 1A, and most of group 2A will do this with water. We'll get the metallic hydroxides and hydrogen gas again. So take solid potassium, for instance, we add that to water. If we think about this being a single replacement reaction this time, writing this as HOH, what we end up with this time when we take that potassium and we replace or take out that hydrogen, what we end up with now is hydrogen off by itself, hydrogen gas again, and the K and the OH are together. Once again, you've got to always be thinking, does anything ionize in this reaction? And KOH is a strong base. Strong base is anything that has a metal hydroxide if that metal is from groups 1A or 2A, except for magnesium. So we've got to rewrite this in its ionized form as K plus OH minus. And in order to get this balanced, we're going to need, it looks like we're going to need 2 potassiums and 2 hydroxides. And then if we do that, we're going to need our 2 waters to balance our hydrogens and 2 Ks to balance our potassiums. So that should balance our reaction now with 4 hydrogens on the left, 4 hydrogens on the right, 2 potassiums on each side, and 2 oxygens on each side. Okay, our last example are some weird bases, amines. Amines are cousins to ammonia. And remember that ammonia we've often referred to as a dirty, nasty hydrogen stealer because it steals hydrogens from acids. That's what makes it a base. So this is exactly what's going to happen if we put in methylamine or ethylamine into water. It's going to act just like ammonia would when it's added to water. It's going to steal a hydrogen. So take methylamine gas bubbled into distilled water. So the methylamine, these are the only 2 I've ever seen on the AP test. So these are the only 2 that amines that we're going to worry about are methyl and ethylamine. So the methylamine is bubbled through distilled water. It's a dirty, nasty hydrogen stealer, so it's going to steal one of the hydrogens from the water. We're going to end up with CH3NH3 plus, because once it steals that hydrogen, that's a hydrogen ion it's stealing, so it's going to gain that positive charge, and we're going to leave behind OH minus. That's what makes methylamine and ethylamine both bases.